Good afternoon, everyone. Okay, so this afternoon, we will continue with Babylonian mathematics, the Plimpton 322, and the contributions of Pythagoras and the Pythagoreans in the field of mathematics. Okay, last time, I pre-recorded a video on Egyptian math, or Babylonian mathematics also, I should say. And then the Plimpton 322, I posted a video over Lens about Plimpton 322. I hope you watched or you viewed the video because it gives very significant information about Plimpton 322. Okay, so what are the drawbacks? Now, going back to your Babylonian mathematics, many of you were sending messages to me about that item in which there were four in a row. Okay, there were 4 in a row of vertical wedges. Okay, instead of 3, because I said before, the vertical wedges or the wedges should be arranged in rows of 3. Okay, however, in that example, I wrote 4 instead of 3. I drew 4 vertical wedges instead of 3 because I said that I lack space. Now, that is one of the drawback. Okay, one of the drawback of your Babylonian numerals. Okay, I'd like you to pay attention to number 2. Okay, this one. Ambiguous use of symbols. You might even encounter some books in which the wedges are not arranged in rows. Okay? They may have it written as just a straight row of 6 vertical wedges or horizontal wedges. Another drawback of your Babylonian numeral is the lack of a sexagesimal point. Next is the absence of 0. Okay? Or no separate symbol. Okay? No, or should I say, a placeholder, I should say. No placeholder. How do we determine whether the first set will be multiplied to 60 raised to 0? The second set will be multiplied to 60 raised to 1. Because there is no placeholder. Unlike our decimal system, if we have 1, 0, 3, okay, automatically that implies that 3 is multiplied to 10 raised to 0, 0 is multiplied to 10 raised to 1, and 1 is multiplied to 10 raised to the second power. So, your numerals, Babylonian numerals, lead to difficulties in determining the value of a number. Okay, that's the problem. Determining the value of a number unless the context gives an indication of what it should be. So those are the limitations of your Babylonian numerals. Now, I purposely gave you or posted that video about Plimpton 322 because this is the single most significant Mesopotamian tablet which evidence Babylonian mathematics. So it says here, it's the most mathematically significant of the Babylonian tablets. And it proves that the Babylonians knew about the Pythagorean Theorem. They knew about the Pythagorean Theorem more than 1,000 years before Pythagoras was born. So in fact, the Pythagorean Theorem was not originally from Pythagoras because there are evidences like your Plimpton 322 which points to the Babylonians as the first to conceive the idea, or should I say the concept of the Pythagorean relationship. Okay? So this is the Pythagorean Theorem which dictates or states the relationship between and among the sides of a right triangle. So that's about your Plimpton 322. Now, some significant features of your Plimpton 322 are the following. It consists, okay, it consists of 15 rows and 4 columns. Okay, 15 rows. Yan. And 4 columns. Let's look at the tree on the right. So the far right is simply the numbering, this one. Okay, refers to the numbering. The next 2 columns are the hypotenuse. Okay, with 4 exceptions. Hypotenuse, 1 leg. So see, these are evidences that Babylonians knew of the Pythagorean relationship even before Pythagoras stated it, or even before Pythagoras proved it. Okay, so line 9, for example, may I encircle? Line 9, okay. 541 is equal to 9, 1 base 60. When you multiply 9 and 1 with the powers of 60, this is times 1 and this is times 60, correct? Okay, so 541. In like manner, for 81 base 60, multiplying each digit by the powers of 60, 60 times 1, or 60 times 60 raised to 0 rather, times 1 is 1, and 8 times 48, okay? 8 times, why 8 times 48? 8 times 60 rather is 480. Okay, 480 plus 1 is 481. Okay, so these are very interesting features of the Plimpton 322. So it also lists down set of the Pythagorean triples. What is a Pythagorean triple? It's a set of numbers which correspond to the integral sides of a right triangle, or 3 numbers that satisfy the condition a squared plus b squared is equal to c squared. Okay, so for example, the least Pythagorean triple that we could think of at the moment is 3, 4, 5. Yes? Okay, because 3, 4, 5, 3 squared plus 4 squared is equal to 5 squared. Okay? 9 plus 16 equal to 25. Can you see this? Okay, so your 3, 4, and 5 are examples of Pythagorean triples. Yet it appeared in an artifact which existed prior to Pythagoras. Yung nasa taas ay hindi nila makita. Okay, so let me write in black then so that it will be visible to everyone. Okay, 3 squared plus 4 squared is equal to 5 squared. Okay, so 9 plus 16 is equal to 25. 25 equals 25. So, this set of numbers is a Pythagorean triple. Okay? So, it's a Pythagorean triple. Next, another example of a Pythagorean triple are the numbers 5, 12, and 13. Okay, you can verify. If you square 5, that gives 25. Yes? So the square of 5 is 25. Plus, the square of 12 is 144. And the square of 13 is 169. If You get the sum 25 plus 144 is 169. Therefore, di po nakikita sa taas. Okay, sige. Okay, so the sum or the left side and the right side are equal. Okay. Now we move on to the next. So you can just go over this. So we could proceed to the work of Pythagoras, or contributions of Pythagoras and the Pythagoreans in the field of mathematics. So now we proceed to Pythagoras. Pythagoras was born between 580 to 572 BC. So, born on the island of Samos, off coast of the modern-day Turkey. Now, there is no reliable information about him. He traveled through Egypt and Mesopotamia, where he probably increased his knowledge of maths, philosophy, and religion. So he left no mathematical writings himself, and much of what we know about him comes to us from the writings of Philolaus and other Pythagorean scholars. So indeed, it is by no means clear whether or not the theorems ascribed to Pythagoras were really solved by him or were really formulated by him personally or maybe his followers. Okay, so he traveled to Miletus, where he made advances in geometry under philosophers and mathematicians such as Thales of Miletus, Anaximander, and Anaximenes. He is considered to be the first true mathematician. So from Samos, he moved to Croton in Italy about 530 BCE. And then he founded a society, a sect, a religion, sometimes it's classified as a religion, named the Pythagoreans, or a group, okay, Pythagoreans, whose main interests were, religion, mathematics, astronomy, and music. Okay, there is mathematics in music. The members were divided into two groups. The first group called mathematikoi, or the learners, okay, who extended and developed the more mathematical and scientific work, the introduction Pythagorean mathematics to Pythagoras himself began. While the akosmatikoi, or the listeners, so two groups, mathematikois, learners, and the akostomatikois, from the word acoustic, listening, okay, listeners, who focused on the more religious and ritualistic aspects of his teachings. So the school he established in Croton in southern Italy was the nucleus of the Pythagorean sect. Now, although Pythagorean thought was largely dominated by mathematics, it was also profoundly mystical. And Pythagoras imposed his quasi-religious philosophies, strict vegetarianism, communal living, secret rites, and odd rules on all of the members of his school, including rules like never urinate towards the sun, and then never marry a woman who wears gold jewelries, and so on. Okay? The universe, or the nature of the universe, according to him, could be explained by numbers and their ratios. And their famous dictum or motto, all is number, or God is number. Okay? Next, we proceed to the next. As a mathematician, he is known as the father of numbers. Okay? Or as the first pure mathematician. And is best known for, you know it very well, the Pythagorean Theorem. okay, which states the relationship between and among the sides of a right triangle. Now, the concept of square numbers, triangular numbers, square numbers, pentagonal numbers that you will meet in a while. Okay? Square roots. Okay. Discovery of the golden ratio. Now, some important milestones in the life of Pythagoras. During his trips to Egypt, Pythagoras probably came in contact with the measuring method of the Egyptians called Harperdonaps or rope stretchers. Now, Egyptians used this for architectural purposes, okay, by tying ropes with 12 equidistant nodes to create right triangles of the lengths 3, 4, and 5. Okay? This suggests that the Egyptians also had some insights about the special case of the 3, 4, 5 right triangle even before Pythagoras proved in a more general version. Okay, some other important information we have to know about Pythagoras. Okay, he believed that everything could be reduced to numbers. And these numbers had their own characteristics. Kaya nga, their motto, all is numbers. And then to him, 10 was the most complete number. Why? 10 was the most complete number because it was made up of the first 4 digits. And when written in that notation, they form a triangle. Can you picture that out? Can you visualize that? Okay, according to him, 10 is the most complete number. Ba't kaya most complete number? Most complete because according to him, it could be represented by, or when, what did he say? It could represent a triangle. So, first 4 numbers are 1. Your first 4 numbers are 1, 2, 3, 4. And if you get the sum, 1 plus 2 plus 3 plus 4 is equal to 10. Okay? 10. So, 1 dot for 1, 2 dots for 2, 1, 2, 3 dots for 3, and 4 dots for 4. True enough. Okay, true enough. If these numbers are represented by dots, okay, they will form a triangular figure. Okay, a triangular figure. Okay, so that's it. 10 was the most complete number because it was made up of the first 4 digits. And when written in that notation, they formed a triangle. Next, he also believed that geometry is the highest form of mathematical studies. Geometry to be the highest form of mathematical studies through which one can explain the physical world. Okay? 3 of the famous works of Pythagoras in the field of mathematics are the following. Number 1, the Pythagorean Theorem. So, the Pythagorean Theorem provides the relationship between the sides, okay, between and among the sides of a right triangle. So, a right triangle consists of 2 legs, okay, and a hypotenuse. And the 2 legs, the meeting point of the 2 legs is the 90-degree angle. Okay? Next. So that's your Pythagorean theorem. A squared plus B squared is equal to C squared. Next. Aside from your Pythagorean theorem, see Pythagorean triples. Pythagorean triples like your numbers 3, 4, and 5. 5, 12, 13. These are the Pythagorean triples. But take note that Pythagorean triples also appeared in the Plimpton 322. Okay? Consists of three positive integers a, b, and c such that a squared plus b squared equal to c squared. Okay? Next, the Pythagorean tetractys. Okay? Tetractys, also known as the decad. Decad, or an equilateral triangle formed from the sequence of the first 10 numbers aligned in 4 rows. Or, that one we have just shown, this one. Okay. This is it. Tetractys. Let me write that. Tetractys. Okay, 1, 2, 3, 4. Kaya tetractys. Now, let's continue. Okay, other contributions in the field of mathematics. Okay, number 1, Pythagoreans. Okay, by Pythagoreans, we mean the followers of Pythagoras. Okay, number 1, Pythagoreans considered the number 1 not just a number itself, but the beginning. Okay, and the dictum of the Pythagorean school was all is number. Number 2, the Pythagoras, and the Pythagoreans the first to recognize even and odd numbers. Okay? Odd numbers, those which are not divisible by 2, and even numbers are the numbers which are divisible by 2. Number 3, we're moving on to number 3. It is found in Aristotle's writing that the Pythagoreans assume 1 as both even and odd. Okay? Is 1 even? Is 1 odd? But it is found in Aristotle's writings that Pythagoreans, the followers of Pythagoras, assume 1 as both even and odd. But if I would ask you now, how would you classify 1? 1 is an odd number. Okay? Next, number 4. Classification of numbers based on prime and composite. Okay? Prime and composite numbers. Okay, let's recall what are prime numbers and what are composite numbers. Okay, prime numbers are numbers having exactly 2 divisors. Yes, 1 and itself. Okay, prime. And composite, those with more than 2 factors. More than 2 factors like 4. 1, 2, 4. 3 factors. Okay, or 3 divisors. Next, number 5. Okay, another contribution in the field of math is the perfect number. Okay, what is a perfect number? Okay, how is a perfect number defined? How do we know whether a number is perfect or not? Okay, a number which is equal to the sum of its parts, excluding itself. Okay? Example of a perfect number is 6. Why is 6 considered to be a perfect number? Because the sum of its divisors, let me write here, the sum of its divisors perfect number. If the sum of the divisors or the factors is equal to the number. Equal to the number. To the given number. So, when is a number considered to be perfect? A number is perfect if, okay? If the sum of the divisors is equal to the number itself. Okay? If the sum of the divisors is equal to the number itself, then that number is a perfect number. For example, okay, let's take for example 6. Okay, let's list down all the divisors of 6. So 6 has the divisors 1, 2, and 3. Take note that when we speak of the divisors, we mean the proper divisors only. Okay, proper divisors. So that excludes, okay, that excludes 6. But 1 is included. Okay, so if we get the sum, 1 plus 2 plus 3, okay, 1 plus 2 plus 3 is equal to 6. So the sum, okay, the sum of the proper divisors is equal to the given number itself. So 6 is a perfect number. Next, other examples of perfect numbers are 28 and 496. Okay, let's look at 28. The number 28. Can you identify all the proper divisors of 28? Okay, the proper divisors of 28 are 1, 2, is 28 divisible by 4? 4, 7, what else? 28 divided by, divisible by, yes. Divided by 2 is 14, yes? Anything else? Okay, so that's it. So if we get the sum, okay, we get the sum of 14 plus 7, that's 21 already. 21 plus 4 is 25. 25 plus 2, 27. 27 plus 1 is equal to 28. Okay? So, 1 plus 2 plus 4 plus 7 plus 14 is equal to 28. Therefore, this is a perfect number. Okay? So, 28 is also an example of a perfect number. It's a perfect number. Now, what if the sum of the numbers is less than the number? Or what about if the sum of the numbers or of the proper divisors is greater than the number? Let's look into 9. Okay, how about 9? Is 9 a perfect number? Let me write here. Is 9 a perfect number? Is 9 a perfect number? How about 12? Is 12 a perfect number? Okay, so let's look at 9. 9 has the divisors. What are the divisors of 9? Okay, 1 and 3, nothing more. Yes? So for 9, the divisors are 1 and 3. So if you get the sum, 1 plus 3 is equal to 4. And 4 is less than 9. Okay, 4 is less than 9. How shall we call 9? If the sum of its proper divisors is less than the given number, there is a special name to that. Okay, we shall call 9 as a deficient number. Okay, 9 is a deficient number. Okay, so when is a number deficient? A number is deficient if the sum of its divisors is less than, okay, less than the given number. How about 12? How shall I classify 12? Is 12 a perfect number? Okay, let's list down also the proper divisors of 12. So for 12, the proper divisors are 1, 2. Is it divisible by 2? Yes. Is it divisible by 3? Yes. Is it divisible by 4? Yes. Divisible by 6? Yes. And nothing more. Okay? So for 12, these are the divisors. Now let's take the sum. If you get the sum of the divisors, 1 plus 2 plus 3 plus 4 plus 6, what is the sum? This is now 10, 15, 16. Yes? So the sum is 16. What can you say? 16 is greater than 12. Yes? So the sum of the proper divisors exceeds the number. The sum of the proper divisors is more than the number. How do we call 12? It's not perfect, it's not deficient, but there is a special name to 12 also. The name to 12, or the how do we call 12 in relation to types of numbers? Perfect, deficient. The other classification is abundant. Okay, so 12 is an abundant number. Abundant number. Okay? Okay, so all these concepts about the perfect numbers, deficient numbers, and abundant numbers, we owe it to the Pythagoreans. Okay, so deficient, abundant, and perfect. I hope that is clear. Now we proceed to the next. Okay, number 6. He discovered also the friendly. Okay, so many interesting numbers. Now, perfect numbers, amicable numbers, okay, deficient numbers, abundant numbers. Now we have friendly numbers. Okay, what do you think are the friendly numbers that we will discuss in a while? Maybe just continue with number 7. Okay, number 7. He discovered the musical intervals such as 4/3, the 4th, 2:3, 3:2 rather, the 5th, 2:1 octave, and proved that musical notes could be translated into mathematical equations. So that's very interesting. Number 8. Pythagoreans observed that 10 contains in it the point, the linear, the plane, and the solid varieties of a number. It is a point, it is a line, it is a plane, and it's a solid. And then number 9, we have the figured numbers, or you may have encountered in the past polygonal numbers or figurate numbers. Let me underscore. Figured numbers. So it seems to go back to the Pythagoras, or to the Pythagoreans, or to Pythagoras and his followers. A dot, okay, a dot is a point which represents 1. 2 dots represent 2, and once joined, they find a straight line. 2 points determine a line, Euclidean algorithm or Euclidean postulate. Now, 2 dots represent 2 and once joined define a straight line. And similarly, 3 dots on the same plane represent the triangle, which is the first rectilinear plane figure. So, 4 dots in the same plane and a fourth outside the plane represent a solid. Okay, so figured numbers or polygonal numbers. And then number 10, he discovered that the sum of any number of successive terms of the series of natural numbers, okay, beginning from 1 makes the triangular number. Okay, series of the counting natural numbers, I should say, okay, counting numbers or natural numbers, okay, makes the triangular numbers. Next, number 11, he discovered the square numbers. So, not only the triangular numbers, but also the square numbers. So, if we have a number of dots forming and filling up a square, then we can get the next square by adding 2 rows of dots around 2 adjacent sides of the original square. I will explain it later. Okay, aside from that, the odd numbers successively added are known as gnomons. Okay, originally, the gnomon was an astronomical instrument used to measure time. Looks like this. Okay, gnomon was also used for a square edge to draw right angles. It's similar to what the carpenters are using. Okay, and developed the theory of means and proportion. Next, number 14, the sum of 3 angles. Okay, the sum of the 3 angles or the interior angles of a triangle is equal to 2 right angles. Okay? The sum of the 3 angles. The sum of the 3 angles of a right triangle or of any, not only right triangle, but any triangle for that matter, the sum of the interior angles is equal to 2 right angles or 180 degrees. Di pala nakikita sa taas, Okay, I should be drawing here. Okay, so the sum of the 3 interior angles of any triangle is equal to 180 degrees. In fact, you can prove that simply by paper folding. You can prove that the sum of the the 3 interior angles rather of a triangle is equal to 180 degrees. Okay, by paper folding. That is a very simple proof to that. By paper folding, we can show that the sum of the 3, okay, so this is already 90 because I prepared a right triangle, 90, and then if I fold, okay, one of the vertices onto the meeting, okay, to the vertex or the meeting point of the 2 legs, you'll find out that another 90-degree angle is formed. So, 190 degree, the original, which is 90 degrees, and then the 2 acute angles, fold them such that they would coincide the third vertex, forming another 90 degrees. So, 290 degrees. 90 plus 90 is 180 degrees. Okay, next, number 5, the discovery of the theory of irrationals according to Proclus. Okay, irrational numbers also, discovery of irrational numbers also could be attributed to the Pythagoreans. Number 16, the Pythagorean triplets, the Pythagorean theorem. Number 17, okay, some other discoveries, okay, theorems involving triangles, circles, parallel lines, and polygons are discovered by the Pythagoreans. Now, let's look into, again, the interesting numbers discovered by Pythagoras and the Pythagoreans. First, perfect number. We're done with this. Okay, perfect numbers. Okay, perfect number. Perfect number n is a positive integer which is equal to the sum of its factors. So let me highlight this, excluding n itself. Okay, so excluding n means the proper divisors only. And the smallest perfect number is 6. Okay, which is the sum of the first three natural numbers, 1, 2, and 3. Okay, can you identify the first 5 perfect numbers? So we have identified 2. The first is 6, the second is 28. Now, I'd like you to verify for 496, 8,128, and 33,550,336. Oh, but this is a huge number. This is a large number. It's difficult to prove already or to do by listing, but there is a proof to this. When you get to your number theory, okay, using some theorems formulated by some other mathematicians, you could prove that this is a perfect number. Okay, in the meantime, you could verify for 496 and 8,128. Okay, so perfect numbers. We're done with this. Next, okay, another special type of numbers we could attribute to the Pythagoreans is the amicable numbers. Okay, amicable numbers. When are two numbers amicable? Okay, but exclude this, please, because there is a different definition of friendly. Friendly and amicable are two different concepts. So, please, may I erase this? Erase natin yan. Now, when are two numbers amicable? Two numbers are said to be amicable if each one of them is equal to the sum of the proper divisors of the other. Okay? So we talk of two numbers, so a pair of numbers. The sum of the divisors of the first is equal to the second number. And the sum of the proper divisors of the second is equal to the previous, is in fact the first number. Okay, let's look at a pair of amicable numbers. Okay, 220 and 284. Okay, 280 or 220 and 284. So the proper divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. If you get the sum of this, you'll end up with 284. Now, if we get also the divisors of 284, proper divisors, and get the sum, you will end up with a sum of 220. Let's show that here. Okay. So, 220. Now, we're moving to amicable numbers. Okay, let's look at the pair 220 and 284. Okay, let's list down all the proper divisors of 220. Okay, what are the proper divisors of 220? Beginning with 1, is 220 divisible by 2? Yes, 2. Is this divisible by 3? No. Is it divisible by 4? Okay, yes. So 1, 2, 4, 5. Is it divisible by 6? And now we have listed it already here. Let me go back to the... Yan. Okay. So these are the proper divisors of 220. 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. So let's just copy 10, 11, 20, 22, 10, 11, 20. May we erase this first? 22. What else have we missed? 20, 22, 44, 55, and 110. 44, 55, and 110. Now, if we get the sum of all these divisors, 1 plus 2 plus 4 plus 5 plus 20 plus, what's this, 11? Bakit na doble? Kamali ako, 11, 20 dapat. Okay, no problem. Plus 11, sobra, wait. Okay, 20, 11, 22. So, plus 22 plus 44 plus 55 plus 110. And this will be equal to 284. Okay? So, the sum is 284 for 220. What about the other number, 280? Now, let's look at 284. Let's list down all the proper divisors. Proper divisors of 284, although it is already identified here, 1, 2, 4, 71, and 142. These are the proper divisors of 284. Wait, let me see. Yes, sorry. Na-erase natin yung 10 dito. Plus 10. Okay? In blue ink. Okay? So, 1, 2, 3, 4. Okay. So, for 284, the divisors are 1, 2, 4, 71, and 142. Okay? 1, 2, 4, 71, and 142. Let's write that here. The divisors are 1, 2, 4, 71, 4, 71, and 142. Okay, let's take the sum. 1 plus 2 plus 4 plus 71 plus 142. What is it equal to? Okay, this is equal to 220. Okay, it's 220. And the sum of the previous is 284. Therefore, 220 and 284 are amicable numbers. Okay? So, this is a pair of amicable numbers, 220 and 284. Next. Another peculiar, interesting pair of numbers are the friendly numbers. Okay, so amicable when one number is the sum of the divisors of the other number. And or the first, so talking about two numbers, the sum of the proper divisors of the first number is in fact the second number, and the sum of the proper divisors of the second number is in fact the first number. So the numbers are amicable. Okay? Dalawa ang 20 ko. Dalawa ang 20? Dito? Ma'am, dalawa yung 20. Saan? Okay, dito. Dalawa ang 20. No. We failed to write 10. Okay, so because we failed to write 10, may we just have it here. Okay, so plus 10. 10 po dapat. Dalawa yung 20. May 20 ba? 1, 2, let's verify. 1, 2, 4, 5. Is this correct now? 1, 2, 4, 5, 20, 11, 10, 22, 44, 55, 10, 10, 1, 2. How many divisors are there? 2, 4, 6, 8, 10, 11. 2, 4, 6, 8, 10. Tama, 11. Okay. Okay. So, amicable numbers. So, going back to friendly numbers. Okay, so for friendly numbers, again, we are talking of a pair of numbers such that the sum of the divisors divided by itself are the same. So the sum of the divisors, okay, sum of the divisors divided by the number are the same. So let's look at the pair of, okay, amicable or a friendly numbers. So 30 and 140. Let's look at 30 and 140. So list down again the proper divisors of 30. 1, 2, 3, 5, 6, 10, 15, and 30. Okay, but proper divisors, did I say proper divisors? Divisors only. Okay, so divisors. So, including the number. But when we talk of, please put this in mind, okay? Reminder, for perfect numbers, checking whether a number is perfect, deficient, or abundant, exclude the number. Okay? So, when we speak of perfect, abundant, deficient, include only the proper divisors. And so, with amicable numbers. But for friendly numbers, the number could be included. Look at this. So, for 30, the divisors are 1, 2, 3, 5, 6, 10, 15, and 30. And when the sum or these numbers are added, the sum would be, okay, the sum would be 72. Okay, 72. Now, 72 divided by 30, 72 divided by 30 in simplest form is this. Okay? Next. How about the other number? What about the other number? 140 this time. The divisors are, okay, divisors of 140 are 1, 2, 4, 5, 7, 10, 14, 20, okay, the 28, 35, 70, and 140. If you get the sum, that will be 336. Now, compare. Okay, what did we say? Yan. The sum of divisors divided by itself. So, 72, let me write it here. 72 divided by the number 30. Is it equal to, okay, 336 divided by the number is 140? Are they equal? Are they equal? Okay? 72 over 30 is 2 and 12 over 30. Yes? 2 and 12 over 30, which is, okay, 2 and 2/5. Yes, 2 and 2/5, which is 12 over 5. Okay, 12 over 5. When simplified, this is equal to 12 over 5. And when simplified, 336 is also equal to 12 over 5. So what can you say? Okay? The ratio of the sum of the divisors to the number itself are equal for both numbers. Okay? So the ratio of the sum of the divisors by itself. Okay? When these are equal, when their ratios are equal, then the numbers are friendly. Okay? Friendly number. So how different is this from the previous pairs of numbers that we have discussed? For friendly numbers, we included the number itself along the divisors, or among the factors or among the divisors. See this? When we listed down the divisors of 30, we have included 30. And when we listed down the divisors of 140, we included 140. Okay? Now, we move on to the next. So, I think the distinction between amicable and friendly, is that clear? Please do not, okay, use one, we cannot use the word amicable and friendly synonymously because they mean different things when we speak of numbers. Okay? Amicable and friendly. Next! Ito yung sinasabi ni Pythagoras na mga triangular, the figurate numbers. Okay, the figurate numbers or figurate number, also known as your polygonal number, figural or polygonal number, is a number that can be represented by a regular geometrical arrangement of equally spaced points. Okay? Equally spaced points. Now, let's look into some of your figurate numbers. The first set here is your set of triangular numbers. Okay? The second set is the set of square numbers. Okay? The third here, your pentagonal numbers. And these are your hexagonal numbers. Okay? Generally, we call them figurate numbers or polygonal numbers. Okay, now let's look particularly into the set of your triangular numbers. So your first triangular number is 1 dot. And then the second triangular number is formed by the first two digits, first two natural numbers, 1 and 2, represented by dots, 1, 2, okay, or your 3. So the second triangular number is 3. The third is 1 dot, 2 dots, 3 dots, 6. The fourth, okay, or considered to be how did Pythagoras call 10? Tetractys, yes, tetractys, or the decad. 1 and then 1 dot, 2 dots, 3 dots, 4 dots. Together, they make 10 dots or a triangle. Then we have 15, 21, and 28. Now, if I would ask you what is the next triangular number, okay? What is the next triangular number? What do you think will be the next triangular number after 20? This is 28. After 28, what is the next triangular number? Is it 36? 36? Most of you responded 36. Now, there is a way by which we can obtain. So that if I would ask you, what is the 100th triangular number? So even without drawing, because that would be taking much of your time, what is the 100th triangular number? You can use your concept of your quadratic function. So let's recall from our quadratic function. So let's show or let's derive, okay, derive a rule that generates derive a rule that generates the triangular numbers. Okay, so that we can easily identify which is the 7th, which is the 10th, which is the 11th, and so on. So, going back, we first copy the triangular numbers, or we don't have to copy, we just tabulate rather. Okay, instead of copying, maybe we just prepare a table of values and let's see how are they related to each other. How are the values or the previous succeeding values are related to each other. And let me use x and y. So let x be number of dots, okay, in the base. And let y be the total number of dots. Total number of dots. Okay, so looking at the first, how many dots are there in the base? There is only one. Total number of dots, 1. So 1, 1. So in your table, in the table, I'll have to write here 1, 1. Okay, let me continue. Go back. So next triangular number, how many numbers or how many dots are there in the base? Base, I mean this. Okay, how many dots? 2. But all in all, how many dots are there? 3. Okay, so 2, 3. Next. Okay, if there are 3, okay, if there are 3 dots in the base, total number of dots is 6. Okay, so 3, 6. Okay, 4. There are 4 dots in the base. There are 10 dots all in all. If there are 5 dots in the base, how many dots are there all in all? There are 15. Okay, so 5 dots in the base. There are 15 dots all in all. So 15. I think we could stop here and let's see what relationship exists between and among the values of x and y. Okay, so may I erase this part now? You know very well that x here refers to the, let me just write so you won't forget. X is number of dots in the base. Okay, sa pinakababa. And y, total number of dots. Because I need this space. I'm going to erase it. Okay. So you see a similar table now. And you dealt with this table when you were in high school. Okay, or in your algebra. Okay. what kind of table is represented or what kind of function is represented by this table. If we look into, okay, succeeding or into differences between y values, getting the differences between y values, 10 minus 15 minus 10 is 5. 10 minus 6 is 4. 6 minus 3 is 3. And 3 minus 1 is 2. So take note that the first differences, okay, the first differences in y are not the same, but there is a pattern. Okay, so 2, 3, 4, 5, what would be next? That would be 6. Yes? Okay, because the pattern is obvious anyway. But if we continue getting the differences in y values, we'll end up with 5 minus 4, 1. 4 minus 3, 1. And 3 minus 2, 1. What kind of function is this? These are the second differences in y. Okay, second differences in y. Okay, so what type of function is shown? Okay, recall from your algebra, anong type of function ito? This is an example of when the second differences in y is constant. How do we call this function? This is a quadratic function. Okay, so this must be quadratic. Okay, quadratic function. It's a quadratic function. Tama? Okay. It's a quadratic function. So, it must behave according to the equation of a quadratic function, which is y is equal to ax squared plus bx plus c. Okay, so that if I would ask you if there are x numbers in the bases, or in the base, sorry, if there are x numbers in the base, what will be y? Okay, so applying your concept of your quadratic function, we can derive a formula for your triangular numbers in terms of this. But we have to find out, okay, we have to find out A, B, and C. So how do we do that? Okay, we have to prepare a table of values similar to this. Okay, preparing a table of values similar to what we have here. Okay, so x, we also prepare a table of values for the general form of your quadratic function, x, y. I hope you could see this. I think it's not visible anymore, so may I transfer to the other page? Okay, so recall from your algebra that y is equal to ax squared plus bx plus c. How about this? Can you see this now? No, ma'am. X, y. Okay, let's begin with a similar table. Since our table here started with 1, since our table began with 1, we will also start with x equal to 1. So we compute for y. So from here, if x is 1, if x is equal to 1, what will be y? Y will be a times 1 squared plus b times 1 plus c. So what will y be? We simplify, what will this be? A plus b plus c. Okay, so what shall I write here? A plus b plus c. Next, what if x is 2. Okay, so if x is 2, if x is equal to 2, what will be y? Okay, y will be a times 2 squared plus b times 2 plus c. Okay? And when simplified further, y will be equal to 4a, you're right, Christine, 4a plus 2b plus c. Okay, so we shall write here 4a plus 2b plus c. Okay, let's continue. How about when x is 3? Okay, when x is 3, what will y be? If x is equal to 3, then y will be a times 3 squared plus b times 3 plus c, which is 9a plus 3b plus c. So what shall we write here? 9a plus 3b plus c. I think we could stop here because our space is no longer sufficient. So I think you have no questions on how we obtained all of this. This is clear? Okay? Because I'm going to need this space. I will be erasing this. Is that all right with you? Or if you want, then I could copy this table in another page. Okay? So let me copy that table in another page so that I could send this anyway, the draft to you. I'll send it or post it in our Lens, in your Lens account. X, Y. So when x is 1, we have A plus B plus C, correct? When x is 2, we have 4A plus 2B plus C. When x is 3, what did we get a while ago? When x is 3, we have this, 9A plus 3B plus C. So let me just write it here. Transfer lang natin. 9A plus 3B plus C. This is when x is 3. Remember, our goal is to find this out. Y equal to A x squared plus bx plus c. What are we going to look for? For A, for B, and for C. Okay? So, like what we did in the previous table, let's get the differences. First, differences in y values. Okay, let's take the differences in y values. 9a plus 3b plus c minus 4a plus 2b plus c is, okay, 5a plus b. Yes, 5a plus b. How about this? 4a plus 2b plus c minus a plus b is 3a plus b. Okay, so these are the first differences. Okay, the first differences. Now, get the second differences. Okay, now get the second differences, although difference lang because we only have a pair. Okay? Isang pares lang kasi tayo, or yeah, 2 pairs rather. Then ngayon, isang pares na lang. Okay, get the difference. That will be 2a. Okay, now, let me copy our previous table. So our previous table has this. When x is equal to 1, y is equal to 1. Okay? From our triangular numbers, when x is equal to 2, what is our y? 3. When x is equal to 3, what is our y? 6. And then getting the differences, okay, getting the differences between y values, 4, 3, 2, and then this is 1, 1. Okay? Okay, now, which means 2a here, the common difference must correspond to 1. Okay? The common difference 2a must be equal to 1. Okay? So let me write that. Therefore, so from here, sulatan natin. I would have to write now 2a is equal to 1. Okay? 2a is equal to 1, which means a is equal to, bakit anong nangyari at nabura ang table ko? So, which means a is equal to 1/2. Okay. So, we now have a value for a. Okay? We now have a value for a. So, we're done with this. Let me put a check mark on a. So, may a na tayo. What else are we going to find? B and C. From where? Okay. From here. The first difference in y is 3a plus b should correspond to 2. Okay? So, 3a plus b must be equal to 2. 3a plus b must be equal to 2. So, let me write that here. 3a plus b is equal to 2. Where did this come from? Once again, 3a plus b should be equal to this. Okay? 3a plus b must be equal to, but what did we find out? Or what did we find out rather about a? A is equal to 1/2. Okay, but a is equal to 1/2. So, this becomes 3/2. Correct? So, 3/2, 3 times 1/2, okay, plus b is equal to 2. Final answer, what will be? B will be equal to 2 minus, okay, 2 minus 3/2 is 1/2. Okay? So, meron na tayong B, meron na tayong A. Ang last na lang ay si C. Okay, saan naman natin kukunin si C? Dito. Okay, the first y value or the value of y when x is 1 in the general form is a plus b plus c. Therefore, it should be equal to this. Okay? A plus b plus c should be equal to 1. Okay, may we have it here? A plus b plus c equals 1. From where did we get this? From here. First entry along y equals the first entry along y. A plus b plus c is equal to 1. Okay? However, we found out that a is 1/2 and b is 1/2 already. Okay? We already found out that a is 1/2 and b is equal to 1/2. So, instead of, or we can now substitute rather, a with 1/2 and b with 1/2 plus c is equal to 1. What will c be? This is equal to 1. 1 minus 1. C is equal to 0. Tama? Okay, 1/2 plus 1/2 plus c equal to 1, which is 0. C equal to 1 or c equal to 0? Which is which? C is equal to 0. So, A here is 1/2. Okay. Okay, 0. Okay, so let me write now on this side of the note, A is equal to 1/2, B is equal to 1/2, and C is equal to 0, we are now ready to generate. Y is equal to A is 1/2 x squared. Remember the general form? The general form of your quadratic function, y equal to ax squared plus bx plus c. So finally, y is equal to 1/2 x squared plus 1/2 x, or simply, okay, x times x plus 1 all over 2. Correct? X times x plus 1 all over 2, because this is equal to anyway to x squared plus x all over 2. And if I factor out x, then I would end up with this. Okay, so if I would ask you, what is the 10th? What is the 10th? Okay, what is the 10th triangular number? What is the 10th triangular number? So from here, now you can use the formula. So the 10th triangular number will be simply 10 times 10 plus 1 all over 2, which is equal to what? 55, you're right. So the first to answer, J mark. Okay, 55. Okay, that's it. Even if I would ask you the 100, the 1,000, nth triangular number, you will be able to give me the, or identify that number. Okay, so this is how we obtain the formula, or the rule that generates. So this is the rule that generates your triangular numbers. Are there questions here? Next, square numbers. For square numbers, the pattern is obvious. Number of dots in the base 1. So if it is 1, simply square 1. Yes? So if the number of dots in the base is 1, just simply square it. Okay? And if the number of dots is 2, you simply square 2 and you'll end up with 4. Okay? So 3 squared is equal to 9. Then 4 squared, okay, 4 squared is 16, and this one 5 squared. So it's easy. So that if I would ask you what is the 10th square number, then you simply square 10. 10 squared is 100. I think there is no question to square numbers. Eh, yung pentagonal numbers, kaya can you try? Okay, pentagonal numbers. 1. Okay. So, for square numbers is simply x squared. Okay? For pentagonal numbers. Okay, let's try with pentagonal numbers. So, for pentagonal numbers, again, just like what we did for square or for triangular numbers, we prepare a table of values for x and y. Okay, so for pentagonal numbers, when there is 1 in the base, total number of dots is 1. Next, when there are 2 dots in the base, the total is 5. So, 2, 5. Next, when there are, let's see, there are 3 dots in the base. 3 dots in the base, we have 12. Okay, so 3, 12. Next, when there are 4 dots in the base, we have 22. Okay, 4 dots in the base, 22. Next, when there are 5 dots in the base, 35 total. 5 dots in the base. Total is 35. Okay? Now, let's check whether this is also quadratic in nature by checking on the differences. Okay, 5 minus 1, 4. Okay, 7, 10. Take note, 13. Yes? Okay, and then when we continue getting the differences, we have 3, 3, and 3. So, common difference, the second differences rather are equal. So, we are very sure that this is quadratic. Okay? Second differences in y values are equal. Therefore, this must be quadratic. So, just like what we had, okay? This is 2a, 3a, a plus b. Look, let me just highlight this. Ito. Okay? So, the first is a plus b plus c. The first entry along the y, okay? The y column rather, or the y row. The row of y is a plus b plus c. And then the first difference is a plus b. And the common or the constant difference is 2a. So, to cut short our solution. So, the common difference, like what I said a while ago, the common difference is 2a is equal to 3. Going back, ito yun. Yan, 2a. This is what I'm referring to. The common difference, 2a, and then we have 3a plus b, and then we have a plus b plus c. So, 2a, and then for this, we have 3, bakit nag-erase? 3a plus b is equal to this, and this here, this one here, is equal to a plus b plus c. Okay? So that we can now proceed to looking for the values of a, b, and c. So we begin from here. Okay, we begin from here. 2a is equal to 3, which means a is equal to 3 halves. Okay, a is equal to 3 halves. Next, we move on to the next equation. Okay, so the next equation is 3a plus b is equal to 4. However, a is 3 halves, so 3 times 3 halves plus b is equal to 4. Okay, which is equal to b is equal to 4 minus 9 halves. B is equal to negative 1 half. Okay? B is equal to negative 1 half. Okay? And finally, C from here, ito. So, A plus B plus C is equal to 1. A 3 halves, B negative 1 half, plus C is equal to 1. Look at this. 3 halves minus 1 half is 1. Correct? 2 over 2. 1 with 1 will cancel out again. This will give you C equal to 0. Equal to 0. Okay? So, finally, we could now set the equation as, again from the general form, y equal to ax squared plus bx plus c, where a is 3 halves, x squared, plus b is negative 1 half, x, plus 0. So, finally, y is equal to 3x squared minus x all over 2. Or in factored form, okay, in factored form, this is the same as 3x times x minus 1 all over 2. And who got it right? 3x squared minus x all. Okay, J. Mark got it correctly. Okay? So this is the rule. Okay, this is the rule that generates the pentagonal numbers. Okay? Are there questions at this point? I think we could end up with this. If there are no questions, the next slide, I'm going to give it as your assignment. Okay? Derive a rule. If there are no questions. Yes, Christine? Any questions so far? Can I leave this as your assignment? 3x? Ah, sorry. Correct. Very good. Na-overlook natin yan. Yan. X. 3 is inside. Okay. 3 is inside. Oh, x only. X only. This is supposed to be x times 3x. Okay? Yes, yes. It's still available. So you can view it even if you are, or should I say, even if the live streaming has ended, okay, it will still be available, so that those who were not able to finish the duration of the lecture, they could still view it for later. Okay. Thank you very much, Christine, for the correction. Did you understand this? Now, your assignment will be derive the, okay? Derive this. Okay, derive the rule that generates the pentagonal numbers. In addition, okay, in addition to that, I want you to identify a pair of, okay, assignment, okay? Additional assignment, I know not pentagonal, hexagonal lang assignment nyo. This is your assignment pala. Hexagonal numbers. Okay? Hexagonal numbers. This, we reserve this for later, or you can just read this. Basahin nyo na lang to. Yan, mga Pythagoreans. Pythagoreans. As fast as I could, siguro, I could just, yes, pentagonal. Hexagonal. Ito ang assignment nyo. Okay, so I leave this as your assignment. Okay? Assignment, derive a rule that generates the hexagonal numbers. And in addition to that, I want you to identify one pair of deficient, one pair of abundant. Okay? So in addition to your assignment, what else will you add in your assignment? A pair, dalawa, of deficient numbers. Okay? Dalawang deficient, tapos a pair of abundant. Pag magkapareho kayo, walang point, ha? Sa dinami-dami ng numbers. Okay? So, ito, derive the rule that generates the hexagonal numbers, and also give me a pair of deficient and a pair of abundant numbers. Okay, questions at this point? Okay, none so far. So the following are the Pythagoreans or followers of Pythagoras. Aristotle, you know very well who he is. Okay, a Greek philosopher who made important contributions in the field of logic, physics, biology, maths, metaphysics, ethics, politics. And then Theon, Also a philosopher who described how prime numbers, geometrical numbers as squares, progressions, music, and astronomy are interrelated. Then Plato. Plato is a Pythagorean. Okay? Best known for his identification of the 5 regular, symmetrical, 3-dimensional shapes. Okay? Or the Platonic solids. Platonic solids, the tetrahedron, octahedron, icosahedron, and so on. Dodecahedron. Herodotus, historian. You know him as, you may have encountered him in your world history. A Greek mathematician and historian, the father of history. Okay? He was the first historian to collect materials systematically, test their accuracy, okay, and arrange them in a well-constructed and vivid narrative. Philolus, okay, most of what we know about Pythagoras are translated to us, or should I say, written to us by Philolus of Tarentum. So, the contemporary of the mathematician Hippocrates, who was the first to write an elements of geometry. We will discuss, or we will study more of the contributions of Hippocrates. That's for later. Okay, classified in, or should I say, in another chapter, Greek mathematicians. Next, the Pythagorean school, as fast as we could na, was a religion. Okay, religion at the same time as school of mathematics. I think I made mention about that before. In fact, Pythagoreans are considered, Pythagoreanism is considered a religion. Okay? Rule of secrecy bound the members to the school. Oral communication was the rule. Okay? Rules for everyday living. Abstain from eating black beans daw. Okay? Not to pick up what has fallen. Okay? Not to touch a white cock, and so on. Not to stir the fire with iron. Do not look in the mirror beside a light. Okay? Pythagorean maths and application. Vegetarianism. I made mention about this already. Okay? Because Pythagoras preached the transmigration of the soul. Transmigration. Okay? Pagpasalin-salin daw. So, in your afterlife, you may transform into a plant or an insect. Yan. Practice probably the not a plant, I'm sorry, vegetarianism, so not touching the insects. Ano? So, parang yung paniniwala ng mga Indians, okay? Ayaw nilang patayin kahit yung mga langgam because maybe daw in their afterlife, they will transform into an ant. I've worked with Indians in the past, and that's it. Okay, so that's all for this afternoon. So, reminding you once again of your assignment, the hexagonal numbers. Sana yung hexagonal? Yan. The hexagonal numbers, pair of abundant and a pair of deficient numbers. For next meeting, we will continue with proofs of the Pythagorean Theorem. There are several proofs of the Pythagorean Theorem. Okay? If there are no questions, then we call it a day. Goodbye, everyone, and thank you very much for participating, and thank you for patiently, listening and watching. Thank you very much. Happy weekend, everyone.